But first, I need to tell you something more about quantum mechanics. Two Hermitian matrices commute if and only if they are simultaneously diagonalizable. And actually, this is a much broader class of matrices than, this is true for a much broader class of matrices than Hermitian matrices. But since not all matrices are diagonalizable, not all matrices are simultaneously diagonalizable. So let's say, let's call these matrices M sub A and M sub B. They're simultaneously diagonalizable. If, so this is the definition, if U, A, U dagger is a diagonal, and U, B, U dagger equals, call it dA, and dB for some unitary U. So the first thing is if they're simultaneously diagonalizable, then they have to commute, because dA and dB are diagonal matrices, so they commute. And if dA equals dB, that implies that UA, or U, well, that implies that U, I'm doing this wrong, aren't I? What I meant to write down was dA equals dB. So that says that U, dA, dB, U dagger is equal to U, dB, dA dagger. And this is equal to U dagger. And this is equal to U, B, A, U dagger. Okay. I am moving too fast and not looking at my notes enough. U dagger dA dBu equals U dagger dB dAu. But because dA was UAU dagger, this is just equal to BA, and this is equal to, well, let's write this one out, equals U dagger U. dA was UAU dagger, so this is U dagger UA U dagger UB U dagger U, which is equal to AB. So AB equals BA if DA, if the matrices are simultaneously diagonalizable. Okay. Yeah, this is the one I should erase. Okay, so now suppose A and B commute. Then U dagger is diagonal. Well, Hermitian matrices are diagonalizable, so there's some U such that U dagger is diagonal. So U dagger is equal to lambda 1 I, lambda 2 I, lambda 3 I. Now, let's look at what U dagger has to look like. I want to claim that it has to look like B1, or B1, B2, B3, 0, 0, 0, 0, 0, 0, etc. So when you diagonalize A, you get the different eigenspaces corresponding to the eigenvalues. And when you apply the same thing to B, you get B1, B2, B3, which are matrices which are just in these eigenspaces. And now you can diagonalize these three matrices because they're Hermitian. And if you apply, U prime I, U prime dagger, you get I. So when you diagonalize these matrices, this matrix doesn't change. So the only thing left to show is why B keeps the eigenspaces of A intact. B must keep eigenspaces of A intact. So that's what happens if we, so let V, I seem to have switched notation. This should be A and B. Let phi be eigenvector of A with eigenvalue lambda. Claim B psi is also an eigenvector of A with eigenvalue lambda. And the proof is A B psi is equal to B A psi, because A and B commute, is equal to lambda B psi, because psi was an eigenvector of A with eigenvalue lambda. So we start with something in the eigenspace of A with eigenvalue lambda, you apply B to it, you remain in the eigenspace of A with eigenvalue lambda. And that says that all of these entries are 0, which means that we can simultaneously diagonalize A and B.